everybody. The program you've all seen.
Okay, let's see, let's put this here. Sorry about this, a little bit of delay.
Our next speaker will also be a follow-up of Garth's initial talk by one of his postdocs, who's now moved on to a wonderful position in Leiden, RychardBouwens. He has a tentative title, so what's the new title? He can tell us the title. So.
Yeah, right.
Richard.
Well, so it's just going to be an extension. But I think, yeah, okay, thanks. What? 3 minutes, whatever. Okay, so this is just going to be an extension of the previous talks. And so one of the themes of Pascal's talk was the buildup of galaxies in the first few billion years of the universe. And I'm going to be continuing with this theme, discussing several different aspects of this, talking about quantifying how quickly galaxies grow, how do they grow up, and whether these growing galaxies can reionize the universe. This is all being done in collaboration with a large number of people from the HUDF-09 team, also grad student in Leiden. So there's a lot of different questions which are of interest for high redshift galaxies. One of the most interesting things to look at with high redshift galaxies is galaxies growth. Galaxy growth is interesting in the early universe since the halos of L-star and sub-L-star galaxies are really assembling down to redshift 3. So we expect the growth of galaxies to be fairly profound. Earlier in this meeting from Pascal and Garth, and in previous meetings from myself, we've advocated quantifying the growth of galaxies in terms of the UV luminosity function. Here are some results that Pascal showed earlier. This is all very useful way of looking at the growth of galaxies, since the UV light really tracks the star formation rate, and this can really tell us something about how rapidly the galaxies form stars and how rapidly that increases with time. However, UV light is also affected by dust extinction, so this may not provide a totally accurate view of how quickly galaxies are growing up. This is particularly a concern at lower redshifts when the dust content is likely much larger. So it's useful to look at galaxy growth, not just in terms of the UV light, but also in terms of the star formation rate. And so instead of looking at the UV luminosity functions, it's useful to look at dust-corrected UV luminosity functions or something like star formation rate function. Fortunately, we can estimate dust extinctions at these high redshifts by taking into account their colors, their colors in the UV, because many years ago there was this nice relationship roughly found between the colors in the UV and roughly the dust extinction. This is this nice statistical correlation which is found to be true for all but the most dust-obscured galaxies at redshift 0 from Murr in 1999. This relationship has been found to also be approximately true out to redshift 2 by Naveen Reddy. Some of this work is basically uses the latest constraints from Herschel, so it seems to work fairly well, at least out to redshift 2. And so given the existence of this relationship and the fact that we can now measure the colors of these galaxies between redshift 4 and 7 from the new WIF3 data on HST, we can now go about trying to quantify, approximately try to quantify the dust correction for these high redshift systems. Again, this is based upon some scalings, but it probably works okay. Okay, so basically if you go out and you look at these large samples of these things and try to quantify the dust extinction in this way, you get the following relationship between dust extinction and luminosity. Basically, the brightest, most luminous galaxies are more dust obscured than the fainter galaxies. So what you can do is you can take this and apply this to the UV luminosity function, say at redshift 4. This is the redshift 4 luminosity function, then you can dust correct it. And the result is the red set of points there. Okay, so this is all being done by Renske Smit, who's a grad student and a PhD student in Leiden. And so these are the results of her paper. So these are the star formation rate functions you get by doing the dust corrections in the way I said. And so basically dust corrections at redshift 7, 6, 5, and 4. It's interesting. So you get this nice build-up scenario where the star formation rate is systematically increasing with time. It's interesting to compare this with the results at redshift 2. The results at redshift 2 are basically from various multi-wavelength studies, basically from mid-infrared measurements and H-alpha type measurements. And what you can see is that following the growth of galaxies from redshift 7 to 4, you can see that if you compare to redshift 2, that redshift 2 is a nice extension of redshift 4. So basically you've got this basically steady growth scenario all the way from redshift 7 all the way down to redshift 2. And so, yeah, this is all very nice. You can also look at this in a simple using one parameter, the characteristic star formation rate, and looking at it from redshift 8 down to redshift 2. And again, you see that it's amazing. It's a nice linear relationship. Here's a blow up of this. And you can see that the dust-corrected UV points basically nicely match up with the mid-infrared H-alpha points down at redshift 2. It's interesting to compare this with the results. If you don't dust correct for dust extinction, you get something that roughly levels off, basically showing the increasing importance of dust extinction. So again, it's really nice that we can get things to work out. It basically suggests that the dust corrections we apply are plausible, maybe approximately right, because we're able to get things to connect up so well. Again, there's lots of, and what we're finding here is very much along the line of what other people are doing, doing theoretical modeling by looking at a lot of the observations and doing, and I'm sure Peter will talk about this in his presentation in an hour or two. So besides the star formation rate function, there's lots of other ways of looking at the growth of galaxies, mass function, UV luminosity function, see Pascal's talk. Well, there's lots of evidence that galaxies are growing quite rapidly at early cosmic times. One might reasonably ask how they're growing. In particular, do they grow through a large number of bursts, or do they grow in a more smooth way? I guess this was talked about somewhat in the question and answer section, but let's just go quickly through my spiel on this. Theoretically, from a lot of the cosmological hydrodynamical simulations, basically there's a tight relationship between galaxy properties and the mass and luminosity. Therefore, as the galaxies are getting bigger, the properties are changing in a systematic way, suggesting somewhat smoother growth. If you look at, for example, the stellar mass versus star formation rate, again, these things are moving somewhat in lockstep, as things are basically growing fairly smoothly with cosmic time, at least in a lot of the models. Some of the lower redshift results, originally from the DEEP team, and here's some more recent work by Stein-White. Basically, there's this nice relationship between these two different quantities. What do we observe in the high redshift universe? Well, before getting on to a discussion of the main sequence of star formation rates, it's useful to look at how various parameters correlate with things like luminosity. And so one thing that's interesting to look at is the UV color of objects. How does that compare with luminosity? Is there a nice, well-defined relationship? And yes, we do find a nice, well-defined relationship. So if you look at the color versus luminosity, there's this nice, effectively, cloud here. And there's this nice correlation between the color and the luminosity in the sense that things are getting redder as you go to the highest luminosities, and they're getting bluer as you're going to the lowest luminosities. The interpretation of this is likely due to the fact that galaxies at the highest luminosities or masses are likely the most dusty. There may be some age effects and some linearity effects, but it's probably mostly due to dust. You find a very similar relationship at redshift 5, 6, and 7 with almost exactly the same slope, suggesting that, again, you have effectively this dust luminosity relationship at all redshifts, and it acts in roughly the same way. You can again see that if you can plot all these things on top of each other, showing the color versus the luminosity, and again, there's this very nice relationship independent of the redshift that you're looking at. You can also look at this as a function of mass. Here's the median stellar mass that corresponds to a given luminosity, so you effectively have a color mass relationship. Again, it suggests that galaxies are growing up somewhat self-similarly. That is, no matter what redshift you're looking at, if you know the luminosity or roughly the mass of an object, you know its color. You can look at other properties of a galaxy. The UV optical color, this is roughly the amplitude of the Balmer break, or equivalently the 4,000 angstrom break, depending on how old an object is or what state it's in. You basically find, again, this very nice correlation between the size of the break and the luminosity. And this is also largely a roughly a dust effect. Basically, we think it's probably also a little bit of an age effect, but mostly dust. So basically, the brightest objects are the most, I show the biggest break, the fainter objects, so smaller breaks. You find this at redshift 4. Parallel slope trend seen in beta. You also find a similar relationship with much larger error bars at redshift 5, 6, and 7. Again, you have this basically correlation between these two different parameters, and you find a similar relationship at all redshifts. Again, pointing to something being somewhat self-similar. So basically the upshot is if we look at a galaxy of a given luminosity or mass at many different redshifts or cosmic time, then its properties are largely determined by its luminosity or mass. And all this was determined as a part of a fairly comprehensive study by Valentino Gonzalez to essentially quantify the SEDs of galaxy as a function of the redshift and as a function of their luminosity. So we looked at things at many different luminosities, and so essentially we could get out all the different trends. Empirically, how do the SEDs of galaxies change as a function of all these different parameters? So once we have how these colors change as a function of luminosity or mass, we can also try to quantify how the luminosity depends on, how the dust extinction depends on luminosity. I showed you these results somewhat earlier. Again, the brightest galaxies are the most dusk obscured likely. Faintest objects are much less. You can also look at the mass to light ratio. This is based upon my work and Valentino's Gonzalez's work. Again, mass to light ratio for the most luminous objects are the highest. The faintest objects, the mass to light ratio is lower. So you can use all these results to essentially come up with a main sequence of star formation rate, figure out how the star formation rate correlates with stellar mass. These are my own results at redshift 4. Here are some results from Ivo Labe from our team at redshift 7 and some work by some other teams essentially trying to do the same sort of thing. So basically, what one finds in all these different studies is that the star formation rate correlates with the stellar mass. One key factor of interest is the proportionality factor between the star formation rate and the stellar mass. So that's roughly the specific star formation rate, which is really the key quantity of interest, which many of you are interested in. How does the star formation rate relate to the stellar mass? And that defines the specific star formation rate. And so this has been of interest to a lot of different people. How does this proportionality factor vary with redshift? At low redshift, it's been known to increase fairly rapidly, but there has been this sort of controversy regarding how does this specific star formation rate evolve toward very high redshifts. And there's been some of a tension between the models and the observations. Well, since that time, we've been working really hard to include things like correcting for the dust obscuration and emission lines, and our results are shown in terms of these green points here. These are from Valentino Gonzalez, and so there's some, even though this relationship is largely still roughly flat, there's some evidence that it is increasing toward higher redshift somewhat. So these are some of the previous constraints, and here are some of the newer constraints from some of our latest work taking into account all these factors.
What has changed?
So here are the changes. The higher values of the specific star formation rate are due to better accounting for dust extinction in high redshift galaxies. And the reason that we can get a constraint on this is basically because we now have width-free measurements. Before, we didn't have good constraints on the UV continuum slopes. And so these are suggesting that there's slightly more dust obscuration in these objects than we inferred before. So this causes a factor of 1.5 rough increase. And we also are correcting for the contribution of emission lines. So there's emission lines from O3, H beta, H alpha, things like this that contribute to, and these emission lines can mimic the impact of stellar mass on these things. So effectively, if you correct for this, the stellar masses go down. So if this is higher and this is lower, this makes this, this causes a specific star formation rate to increase.
What factor increase does that number 2 give you for line correction?
It's roughly 1.7 or so, but there's a competing effect that even though it increases the emission lines, causes the masses to go down, it turns out that the specific star formation rate is inversely correlated with stellar mass. And so that basically somewhat compensates for this. But in any case, it turns out if you take both of these things into account, it causes it to somewhat increase. Yeah, well, here it's a big factor, but the error bars are large. Here, if you look at this, it's still a factor of roughly 2, maybe somewhat less than 2. But anyway, this is obviously going to be a quantity. This is going to be something that observers work on, going forward. So there's going to be quite a bit of effort put into this, although it is very challenging. So thus far, I've told you the SED shapes of galaxies are largely self-similar, depending on only luminosity and mass. This is not entirely true. There is scatter in the property of galaxies at a given luminosity or mass. So, this basically the relationship between beta and luminosity isn't infinitely narrow. There's some scatter here. Also, the relationship between the inferred mass to light ratio and luminosity isn't infinitely narrow. There's also some scatter here. So this scatter points to some non-uniformity in the star formation history. But again, I think it's going to require a fair bit of future modeling to figure out what all this might mean. So again, a lot of the going forward and important goal going forward will be to quantify these variations much more accurately. One other thing that we've noticed is not only is there scatter in these relationships, but it turns out that some of these quantities aren't completely independent of redshift. The UV slopes in particular show some modest dependence on redshift. Basically, the UV continuum slopes become bluer toward the very highest redshifts. And I'll just skip over this. Previously, there was some controversy about this, but basically, based upon some early work, but now people are tending to converge, and basically it turns out that the measurements that people are getting for the UV continuum slopes, they're not so blue as to suggest exotic stellar populations, but you still get this color magnitude relationship with colors about as blue as you could get before exotic stellar populations. Again, it's suggesting there's very little dust in these systems. Okay, I won't have much time to talk about this, so I'll just try to hit the high points. Reionization of the universe. Can growing galaxies reionize the universe? How can we answer this? Well, we have good constraints on the UV luminosity function out to redshift 10. We can extrapolate these current measurements to higher redshifts and lower luminosities. And we can make reasonable assumptions about various properties of the galaxies, like the escape fraction and the clumping factor for H1. And to see if we can explain reionization, we have to match the observations. Like, we have to reionize the universe roughly by redshift 6. We have to match the Thomson optical depths observed by WMAP, and we have to match other observables. So how many ionizing photons do galaxies produce? It's very easy to calculate the contribution from bright galaxies, because you can just integrate out the luminosity function. The faint galaxies are more challenging, because you essentially have to take this and extrapolate it. And you extrapolate it based upon the faint and slope to include the part that you can't see. This extrapolation, or this correction factor for this extrapolation, is very dependent on the faint and slope, as shown in the following plot. Basically, the correction factor could be anywhere from a factor of roughly 2 to 3, all the way to a correction factor of around 12 or 13. This is the current determination at redshift 7, and as you can see, the 1 sigma error bar, the correction factor, there's a huge range. So, and you can see how important this is to pin down. So there's been a lot of attempts to pin this down at high redshift. This is the faint and slope versus redshift. A lot of determinations from our own study and 1 or 2 other studies. And so, again, there's some slight hint that the faint and slope may be steepening. So you can try to take this steep faint and slope, say it's not evolving, and then see if you can match the observations. Say if you take a steep faint and slope, no evolution. And so you find a reionization at redshift 7 and a moderately high Thomson optical depth, although this value falls short of the WMAP value. Alternatively, you can assume the faint and slope is becoming steeper toward higher redshift, as Gar showed in his presentation, and as somewhat tentatively supported by the observations. If you assume the faint and slope is getting steeper toward higher redshifts, using this sort of scenario, you can fairly comfortably match the Thomson optical depths observed at high redshift. Although, again, we'd like to have better constraints on how the faint and slope is evolving. Again, the potential steepening of the faint and slope may be important for explaining the observed Thomson optical depths. And you can see this by plotting the the inferred Thompson optical depth versus the steepening, the rate at which the Feynman slope is steepening with redshift. And with just a little bit of steepening, you can easily match the WMAP values. There's a lot of other things that we want to match, things like Lyman alpha constraints and the ionizing photon injection rate, the kinetic SC effects. There's a very nice paper by Mike Coulin he essentially goes through all these different constraints, and he looks at a lot more things than we even do in our papers. So I'd again suggest that if you really want to understand more about this, you look at Mike's paper. And I'm basically done with the presentation. Mike also looks at a lot of other things in his presentation and his paper, but I'm not going to go into that. So anyway, here's a quick summary. I'm way over time. I guess the key points are, in order to quantify galaxy growth, I suggest you look at the star formation rate function. I think the results are quite nice, and they're very useful to compare with a lot of the current theoretical results. We find these nice color magnitude relationships between things like the UV continuum slope versus luminosity and the UV optical colors versus luminosity. The uniformity of these relationships at all redshifts suggests that galaxy growth is largely self-similar. And I think that's all I'll say here. Okay.
We're technically over time, but I think we can take a few minutes out of our break in order for a few questions for Richard. Any? Stein.
I was wondering, when you said exotic stellar populations were needed to explain the Atlas slopes, do you have any constraints on the melicities, like how low they could be?
Any direct constraints? I think we have very poor constraints on metallicity.
Like with exotic stellar populations that you didn't need, do you?
Well, basically from the colors themselves, we have no constraints. I mean, to get tight constraints on metallicity, it'd be useful to have spectroscopy and high resolution spectroscopy. It's very difficult to get any direct constraints on without having a gravitationally lensed object, which is magnified by a factor of 100. I think it would be very difficult to come up with any direct constraints on metallicity. Maybe if you look at maybe some gamma ray bursts or some other things, but I mean, again, we were trying to use colors as some way of getting at this issue, but you need fairly extreme colors, that you've measured very, very robustly to have any sense of that. And again, that effect may be degenerate with other effects, like if the escape fraction is higher. So there's, it's very difficult to get direct constraints on that from current observations.
Sandy?
Could you just summarize briefly whether you think there is or is not any tension anymore between the masses and the star formation rates that you are measuring at higher redshifts and estimates of the stellar mass in the universe at CU2?
Let's see. I don't believe there necessarily is. I haven't looked at this. In detail. But looking at the plots that Pascal showed earlier, and looking at plots in many other papers, I don't see any evidence that there's any fundamental discontinuity between the stellar mass results at redshift 2 to 3 and the stellar mass results at redshift 4 to 6. Maybe there's some study that you're thinking of that I'm not thinking of right now.
Yeah, sure. A few years ago there was a disconnect of a factor of 2 or something.
Oh yeah, the Wilkins results. Well, those results have been subsequently been revisited. Naveen Reddy looked at this in a very nice paper. And he found in that study that if you self-consistently consider the star formation rate density and the stellar mass density to the same mass limit or luminosity limit, then he found no problem. And so there may have been two issues with the Wilkins study. One of the issues was that it's possible that they weren't considering the star formation rate density and the stellar mass density to the same luminosity or mass limit. So maybe they weren't doing the integrals to the same limit. And number two, basically the dust corrections you infer by integrating to very low luminosities are basically much less than you would infer if you just looked at L-star galaxies. So instead, typically for the brightest galaxies, you have dust corrections of 5. But if you integrate, if you actually consider the dust corrections integrating all the way down to, say, to very faint, to very low luminosities, the dust corrections are maybe closer to a factor of 2 to 2.5.